I now start with the general power function. Before that, let me take up this case. When I talk about this case, limit extending to infinity ln x by x, here I see in the numerator and in the denominator that as x tends to infinity, both the numerator and the denominator, they tend to infinity. So I get an indeterminate form of the type infinity by infinity, and that's exactly what I've written after this. This means I can apply L'Hopital's rule. When I apply L'Hopital's rule, I differentiate both the numerator and the denominator with respect to x, and eventually I get 0 because of that. That means ln x by x tends to 0 as x tends to infinity. Now let me get to the general power function. So if we can recall, we have done this in chapter 4, that for all real numbers a, when I say real numbers, that means both rational as well as irrational. For all real numbers a, if I have f of x equal to x raised to the power a, this implies f prime x is equal to a multiplied by x raised to the power a minus 1. There we did not think of the irrational values of a. Now we are going to actually think of both the rational as well as irrational values, and let's try to take up x greater than 0. If x is greater than 0, we can actually give such a definition for x raised to the power a, even for irrational values of a. So there we did not define x raised to the power a for irrational values of a, but now we are going to give such a definition for x greater than 0, but we are going to take up all values of a, even irrational values of a. So in this case, I can write x is equal to e raised to the power ln x, because ln x is nothing but the power to which e has to be raised in order to get x. Keep this in mind that we are considering x greater than 0. This is precisely because I have written ln x here, and we know that the domain of the natural logarithmic function is 0 till infinity, 0 not included. I can write x is equal to e raised to the power ln x, and that means if I have x raised to the power a, keeping in mind the fact that a consists of all real numbers, that means rational as well as irrational. So this is equal to e raised to the power ln x raised to the power a, and that means it is e raised to the power a ln x. If I now want to differentiate x raised to the power a with respect to x, I can go for this d over dx of x raised to the power a. This is equal to d over dx. Now x raised to the power a can be written as e raised to the power a ln x. Now we can also apply the chain rule. That means this gives us e raised to the power a ln x multiplied by a by x. Now e raised to the power a ln x can be written as x raised to the power a. That means I have x raised to the power a divided by x, and that gives me a multiplied by x raised to the power a minus 1. So we have now proved the differentiation rule even when a is an irrational number.